Welcome to another podcast. This episode, we're going to be taking a look at geometric series. There's a lot of information that's going to be jam-packed into this podcast, and it's actually one of the more important topics we're going to get to in Chapter 11, dealing with geometric series. There are two basic forms that the geometric series can take, or that we will see it in, although there's technically a lot of forms. The most basic form that we see geometric series take is n equal to 0 to infinity of ARN. And if you start to write out the terms, this is just when n is 0, you get a plus a times r plus a times r squared plus and so on. There's a couple of key terms associated with these series that we'd like to discuss. The first is that a is called the initial value of the geometric series, and r is called the common ratio. Now, the way that you determine r is you can see that each successive term, to get the new term, you just simply multiply by r. For instance, here, if I was to continue this out, the next term would be r times the previous term. So it would be ar squared times r would be ar cubed. So r is called the common ratio. Now, you can also write this same series starting with n equal to 1. And when you do that, you would write it as ar to the n minus 1 instead. So understand that both of these formulas are used to describe a geometric series. You can look at it in this form, or you can look at it in this form. It just depends on whatever your starting index is. There's nothing different about the two series, but there are advantages and disadvantages to each representation, and we'll kind of talk about that as we go through. I'm going to start by looking at the partial sum. So I'm going to look at Sn, the partial sum sequence. So this would be the sum n goes from 0 to capital N of ARN, which if I write out the terms would be like this, all the way up to a power of n, capital N. And I'm going to take and multiply the partial sum here by r, by the common ratio. When I do that, I'll get AR plus, basically I'm just going to raise the power of all the r's by 1. Now, the reason that I'm doing that is I'm after a formula for Sn. I want to know what my sequence of partial sums looks like. Remember, that's the only way I can tell you what the sum of a series is, and that's what we're after here, is to figure out the sum of the geometric series. All right, I am going to subtract these two things. So I'm going to take Sn minus Rsn. So Sn minus r times Sn will be equal to, now I'm just going to subtract each of these terms. So a minus this, minus this, minus this, and so on. And what you notice is a has nothing to subtract with, so it's just a, but then you have ar minus ar squared minus ar squared. All of these cross terms, even this one, will cancel out, and you'll be left with just minus ar to the n plus 1 if you subtract those two things. Well, the nice thing about this is I can factor out an Sn from the left side, leaving me with 1 minus r times, and then factor out an a from the right side, giving me 1 minus r to the n plus 1. Remember, I'm trying to solve for the partial sum, so the partial sum is given to me by this formula. Now, this is actually a pretty important formula. We're going to be using this a couple of times in this video and a couple of times in class. So you'll definitely want to commit this formula to memory. It's going to have excellent use in other courses as well. So this is the partial sum formula for a geometric series. All right. Now, one of the interesting uses of this is to determine if we possibly have a sum to the series. So remember that if a sum exists, so if this guy is equal to some value s, then that's going to be equal to the limit of this sequence of partial sums. But we now know the formula for the sequence of partial sums is a1 minus r to the n plus 1 over 1 minus r. And it's just a question of whether or not I can take that limit. So doing a little bit of work here, I'm going to separate out two terms. I'm going to separate out a times 1 over 1 minus r minus a times r n plus 1 over 1 minus r. And the reason I'm going to do that is the limit will ignore this first term, because this first term does not have a capital N that it's a part of. So instead I can take the limit of this second term, and so we have a 1 minus r, and the question is, what does this second term become? Well, there are two possible avenues here. If r is less than 1, so if this value here is less than 1 in absolute value, so if the absolute value of r is less than 1, the result of this limit is as n grows larger, this power grows smaller, so the limit of that term is 0. If, on the other hand, the absolute value of r is greater than or equal to 1, then this term will stay large, and what will end up happening is as n goes to infinity, you have a higher and higher power here, so this will diverge to infinity. It could be plus or minus, depending on if r was positive or negative. Now I'm including equal to 1 here, even though strictly speaking, if r was 1 in this case, it wouldn't be too bad. It's just you have the 0 in the bottom, so I'd have to come up with a different way of determining the limit. But you can clearly see over here that if r is 1, then I'm adding up an infinite number of terms. For example, if r is 1 here, you can see that my partial sum, if r is 1, is just n times a. So when r equals 1, Sn is simply n times a, and as n goes to infinity, this would also go to infinity. So r equal to 1 is not allowed either. The upshot of all of this is we end up with an answer, but only in the case where the common ratio in absolute value is less than 1. So summarizing this, basically what we have is that the sum of the geometric series is given by this formula a over 1 minus r, precisely when the absolute value of r is less than 1. Or the sum is equal to, well, it diverges. It's going to be either plus or minus infinity when the absolute value of r is greater than or equal to 1. So these are the two possible cases. This is a very important result, but these are the two possible cases for the geometric series. Now I want to take the opportunity to do a couple of examples with this, and so I'm going to try to leave up these formulas as best I can. All right, so now that we have some room cleared out, I want to look at a couple of examples that use these two formulas. The formulas I'm talking about here are the partial sum sequence here and the sum formula for the geometric series here. So the basic example I want to start with is just using the sum formula. So let's suppose that I asked you to find the sum, n goes from 0 to infinity, of 4 over 3 to the n plus 1. Well, if you write out the first couple of terms of this sum, you get 4/3 plus 4/3 squared plus 4/3 cubed, and so on. And hopefully you can recognize that the initial value here, a, is 4/3, and to get from each term to the next, I'm having to multiply by 1/3. So multiplying by 1/3 will give me the next term. This suggests then that for this series, a is 4/3 and r is 1/3. So if I use my if I use my sum formula, the sum should be a over 1 minus r. And the reason I know that I can use this part of the formula is this in absolute value is less than 1. So I know I'm in the case where this series will converge. And so the formula here would be 4/3 over 1 minus 1/3, which ends up being 2. So I know that after I get through adding up all these infinite number of terms, the sum will get closer and closer to the value 2. So 2 is considered to be the sum of this infinite geometric series. All right, also, I want to take a look at using the partial sum formula. So with the partial sum formula, what you have is a slightly different example that I might want to use. So looking at this same sum, I might want to ask the question, what is S20? Well, if you look at how we've defined things for Sn, remember Sn is, for this case, we defined this formula. This was the formula we used for this version of the sum. If I used a different version of the sum, so if we used this sum instead, what would the partial sum formula have been? Well, Sn would be equal to the same thing, but our value of n would be 1 less. So rather than have n plus 1 here, I would have n here. And so we would end up with the partial sum being of this form. So that's why I highlighted this red to begin with. It's not the formula I would prefer you use. Rather, I would prefer you use this formula as your partial sum formula. And the reason that I would rather you use this one is when I ask what is S20, typically we infer that S20 means the sum of the first 20 terms. But here, if I used S20 for this one, then because this starts at 0, this is A0, A1, A2, and so on, S20 would actually end up being the first 21 terms. And so I want to be very careful about that, and that's why this partial sum formula is the better one to use, because this will literally give me the sum of the first 20 terms, because the first term is numbered 1. Right? We start with term 1 instead of over here where we start with term 0. So the upshot of all of this is I want to find S20. S20 would be, once again, I'm talking about this particular example. So S20 would be, I'm using this formula, A was 4/3, so it would be 4/3, 1 minus r, which is 1/3, raised to the n, well, n is 20, since it's the 20th term sum, divided by 1 minus r, 1 minus 1/3. If you calculate this, you'll get approximately 2, which is not surprising given that 2 was the sum of the entire series, and we're taking 20 terms, so we're likely to get very close to 2 at that point. But what I want you to understand is if you wanted to get the same answer here, if you wanted to get exactly 20 terms using this formula, you would have to do S19. So I'll do it in red just to illustrate. S19 in this formula would be 4/3 because A is the same. 1 minus r, r is 1/3. But then I'm raising it to the n plus 1 power, so S19 would be n plus 1, 19 plus 1 or 20, 1 minus 1/3, and that would give me the same approximate 2 that I got here. The difference is it's more natural to say S20 is the sum of the first 20 terms than it is to say S19 is the sum of the first 20 terms. And it just all has to do with the difference of starting at 0 versus starting at 1. Now, I know I went into a lot of detail here on different things, but honestly, the thing to take away from this video is these two formulas. You need to know these two formulas for the sequence of partial sums, and if your sum is started at n equal to 0, then this is the formula to use. But if you're looking at your sum starting at n equal to 1, then this is the formula to use. But I recommend each of these two formulas as the ones to look at. We're going to do another video here where we're going to have several more examples of geometric sums being added up. But I wanted to go into some of the details about how we arrive at these two formulas and how we're going to use those two formulas in future videos. All right, thank you for watching.